Okay, I'm going to get started again. Hopefully that was at least 5 minutes. So I'm going to start with an overview of sort of the internet architecture and sort of the principles behind how the internet was developed. And the reason why I want to look backwards, I mean, this is in the 1960s and 1970s we're looking at. The reason I want to look backwards is that it actually provides you a story that you can apply to the cloud to see where that thing is going. And so it's like eventually there will be a computer history degree here at Portland State, and I might actually be the one to offer that degree after I'm too old to figure out what the new hotness is doing. I'll teach this history course, and this is the first start of it. To go back and think about what made the internet successful, you can go back and there's a lot of different reasons that the internet became the one data networking standard that all of us use. Could you imagine trying to unify the world on a single protocol? That doesn't happen, right? Like, we can't agree on anything. Like, even in this university, getting multiple professors to agree on something really silly, it's like, yeah, it's the worst. So can you imagine unifying the entire world on an internet, a data networking protocol? And so if you look at what happened, it actually informs how you would go about disrupting the cloud, because it's a very similar situation that we're coming across when we look at cloud and cloud providers like AWS, Google, and Azure. Okay, so we're going to talk about packet switching over circuit switching, the end-to-end principle in the Hourglass design, and layering of functionality. And I think that these three things are really driving, they really help drive the adoption of the internet protocols. So the first thing is packet switching over circuit switching. So what is this? I like to use an analogy. And the analogy is ride-sharing vehicles versus privately owned vehicles. So you have your Zipcar, your Car2Go. Actually, did they go out of business? One of these, I think Car2Go just, no, it was that other one. Forgot the name. But anyway, one of them went out of business. Or any of these scooters, Lime, Bird, Skip. So the idea is that you have many users and there's a single car or a single scooter. And whenever you need it, you just get a scooter and then you use it. If you have a large amount of demand for that resource, then you get users delaying their usage. But the big benefit of this, and this is why it's making money, is that you more efficiently use that resource, right? It's more cost effective for you to just do this than to actually own one of these things yourself and for you to use it like once a month. Okay. This is in contrast to privately owned vehicles, which is the circuit switching model. In the circuit switching model, you have a single user who owns the resource, and it's guaranteed access for that person. Whenever that person needs it, it has access to it. So this is the cost for owning it, or this is the benefit you get by putting up the cost for owning it. But the vehicle isn't used as efficiently. Like, I have a car at home, and nobody uses it during the week. You use it on the weekends. So, does anyone know what these are pictures of? The old telephone network. Yeah, all right. This is circuit switching. This is the way we did networking back in the day, in the early 1900s, right? So, and you can see, this is a plug board, and they're taking plugs, they're figuring out who the source caller is, figuring out where the call is going to, plugging in. That is a circuit being made, and it's it's like a physical wire going through. So that's circuit switching. And so this was the phone network pre-cellular. Right now, all the cellular networks are doing packet switching. So this is like, it's a long time ago, but this is like one of the only circuit switch networks around. And well, actually, even now, your wired phone is packet switched underneath. So as it turns out, it's hard to find a circuit switch network, basically. So the model of the phone network is an end-to-end reservation, an end-to-end resource allocation is made from the source to the destination. So you're establishing that, and that's where those people were actually establishing that circuit. So the end-to-end resource is divided into pieces and reserved for the calls that are going through it. The link bandwidth, the switch capacity, all of those things are dedicated for that particular call. If you establish this circuit, but then you don't say anything on that line, nobody else can use that bandwidth anyway. It's dedicated for you. So no sharing. But the nice thing about this, and the reason why they had to do this for the phone network, is that you needed guaranteed performance. We figured out that a voice stream, in order to be legible, or in order for you to understand it, you needed it at least 56 kilobits. That's basically the minimum before it starts getting sort of not enough for you to reconstruct what's going on. So they needed this 56 kilobit, actually it was less than that, I think it was half of that, but they needed a small kilobit guarantee on an end-to-end basis, and they knew all they were doing was routing voice calls. So they knew the application didn't need anything else. And that's what you ended up with. Packet switching blows all of that up. You don't divide bandwidth into pieces. You don't have any dedicated allocation. You don't do any resource reservation. When this was proposed, when the phone network was the dominant network, when this was proposed, people thought the guy was crazy. Like, are you kidding? You can't build a network out of that. That'll never work. And that guy was Leonard Kleinrock in 1960. He was like, hey, the military wants to build a data network. They're trying to figure out how to build the network components. I think they should build it using packet switching. And this was the revolutionary sort of idea in 1960. The idea here is that packets share the network resources. Each packet uses the full link bandwidth. Whenever you send the packet, it gets everything. But when that particular node is not sending that packet, some other node can send a packet and use its full network bandwidth. Okay? But the big problem here is that you get congestion, right? It's just like the ride-sharing situation. And so if that happens, then you basically have packets queuing, you have packets being lost in the network, you have all sorts of issues that you would see in the internet when I was using it in the 90s. Maybe not so much for you because the bandwidth here is way better. So packet switching versus circuit switching. This is a picture that shows you the benefit. So if you have and you see this really dates me. So this figure is from the 90s when 1 megabits per second was actually a lot. Now I think it's like you're getting like 50. I think Comcast gives you 50 now as like the starter package. Used to be just 1. Actually, this used to be 1 just for universities like us. We would get 1 megabits. But if you had end users sharing this 1 megabit per second link, and say that for each user, they're active 10% of the time, and they use 1/10 of the link, so 100 kilobits per second. If you had a circuit switch network, you would only be able to do 10, right? Only 10 users can use that thing. If you use a packet switched network, and they're active 10% of the time, well then it's probabilistic whether or not you get more than 10 people active at the very same time. And in fact, with 35 users sending 10% of the time, the probability that you can get 10 users simultaneously active is this vanishingly small percentage. So this is what we call a statistical multiplexing gain. It allows more people to use that network than the old circuit switching model. This is what really sped up the adoption of packet switching. Because then this statistical multiplexing gain allows you to accommodate a lot more machines onto the network. Okay? This is the basis for the cloud. This is where major cloud deployment started. It began with Amazon packaging things up for Christmas. It's like, God, there's a lot of people ordering stuff in November and December. I better buy a ton of servers to manage this load, otherwise I'm going to be losing money. And then January comes along and like, God, I have all these servers. I have nothing to do with these servers. What am I going to do? I'm going to let some other people rent my computer. So that is and this happened in the probably early 2000s, this happened. And that is basically the reason. You're getting a statistical multiplexing gain, not on the network, on the infrastructure, on the servers, right? Now a lot of people can use that server, and then there's only one outlay of capital costs. Okay, we'll revisit this when we get more to the cloud part of the course. Okay, so is packet switching a slam dunk winner? Well, it's great for bursty data. It's simpler because you don't have to reserve anything. But it's bad for applications with hard resource requirements. So in the early days of the internet, we barely had enough to support a 56 kilobit per second connection as far as a data network connection. So voice over the internet was awful. It was terrible. Like if you tried a voice call in the 90s over the internet, you could barely hear anything. And so because this congestion gives you this packet delay and loss, it made these applications unusable. But we adapted. So this is where a lot of the innovation came about. A lot of the protocols and the applications on the end adapted to the use of the to the limits of the network in the middle. And this is where a lot of the internet protocols began to be developed. A lot of the modern ones that we see today were developed out of this. To be able to operate on a network that's got all sorts of packet loss, all sorts of packet delay, how do you get applications that are built on top of that? And you'll see the protocols when we do our sprint over the protocol stack, what they have done to address this. Okay, the second thing is the end-to-end principle and the Hourglass design. This is a picture of the Hourglass design of the internet protocols. And so there is one single network protocol that runs everything, pretty much everything. There's vanishingly small numbers of things that don't use IP. And so I like this quote, where perfection is achieved not when there's nothing more to add, but when there's nothing left to take away. I think that actually applies, maybe a couple things you could take away from IP, but IP really is the minimal possible things you could implement to get data connectivity. And so, we're not going to go through everything that IP has to offer. There's not much. But the end-to-end principle states, the idea of that is, where are you going to put functionality? Are you going to put it at the edges, or are you going to put it in the network? If you decide to put it in the network, then your protocol in the network is going to be big, right? You're not going to have a narrow waistline. You're going to put all this functionality in the middle. So the end-to-end principle says you don't want that. You want to avoid that as much as possible. So what it says is that the end-to-end function is best handled by end-to-end protocols. If at all possible, you can implement that functionality at the endpoints. That's where you put it, and you take it out of the middle. You take it out of the network protocol. And this was the core design principle of IP. Right? This drove it all. And you're like, in fact, either that or laziness. It's like, I don't want to implement all of this stuff. This is my course project, and I want to do very minimal to get an A. This is basically, so this came out of UCLA, part of this. So you're like, what is the minimal thing that we can get to get these things to work? And then you'll see, oh, we have IP. And then the idea is to really put all the intelligence and the applications at the edge of the network. Okay, so this leads to innovation at the edges, and it's a complete opposite image of the phone network. The phone network has dumb edge devices and an intelligent network to do all the services that the phone network was providing. The internet is the opposite. The internet has a dumb network, and all the stuff on the outside is collaborating to give you an intelligent service. So it's the opposite. Okay, so this leads to the Hourglass design. So there's only one protocol at the internet level, and that's IP. And if you look at IP, it's an unreliable datagram service. It gives you addressing and connectionless connectivity, and this is very much like the post office, the US post office model of communication. Okay, so the benefit of having a super simple design in the middle is that you get fast deployment. And so IP took off because it was really easy to implement. In fact, the RFC that standardized all the things in IP, it's like a dozen or so ASCII text. It's an ASCII text file, because back then all the RFCs were text files, and it was like a dozen pages, right? This is what you need to implement. At least one of the IP RFCs. There are some other ones. The main one was a dozen or so pages. This allowed you to implement this very easily, because there's not that much to implement. It also was important because at the time in the 70s, the semiconductor technology in the 70s was really primitive. You could not build a lot into one of these networking devices, and if you tried to have that networking device do too much, it couldn't process packets very quickly. It cratered your bandwidth. So this was really important, that packet processing was basically minimal. There was minimal overhead. And the last part, when you have a bunch of vendors rapidly developing and deploying this thing and building things, you'll get economies of scale. As soon as you get economies of scale in technology, the thing is going to take off. And that's what happened. Now people were focusing on building IP routers, and were able to get the price point way below the other data networking vendors that were doing other standards. There was like 3 or 4 other major data networking standards at the time, and this really caused the thing to just go all to IP. Okay, one of the interesting things about IP is that it's designed completely independent of hardware. You had all these people with proprietary platforms for their hardware, and IP says, you know what, I don't care about what the hardware says, I'm going to have an abstraction that decouples my networking layer from your proprietary stuff underneath. This is important when we get to the cloud, because there's a lot of proprietary stuff in the cloud. So this is a key point here. You don't need to buy a particular vendor's hardware in order to participate on an internet network. So that's big. And this allows IP to run over any fabric. Okay. So the translation to the cloud. So right now we have all these major cloud providers, and they're all trying to lock you in, right? They want, like AWS doesn't want you to go and move to Azure or Google, and the same thing with the other ones. So what technology can you think of that might allow applications to run on any cloud provider without having to like lift and shift your stuff out of there? People are having a hard time even lifting and shifting their stuff into the cloud, let alone between cloud providers. But be sure that this is something very important. And this is important for companies. Any company that you work at that's locked into one cloud provider is going to want a strategy for when that cloud provider decides to increase their price by twice as much. They need a strategy to be agile, to move away, right? And this is the new hotness. Trying to get multi-cloud, trying to get interoperability at the cloud layer. And this is why, if you look back at the way the internet protocols did it, you're like, okay, there's a model, and this is the model that actually Google is following, that we'll get to later on in this course. Okay, so the good thing about the end-to-end principle and the Hourglass design is that the basic functionality allowed the thing to be adopted very quickly. You have deployment using very simple devices. The bad thing is that any of these new network features that you want to build, you have to change a whole bunch of routers, right? And so it was really hard to get any sort of widespread adoption of things that made a lot of sense, like IP multicast. Why do I have to send a copy of this video that everyone is watching to multiple servers and then make multiple copies to multiple users on the back end? Why can't I have a multicasting protocol that's built into the network, right? So that was one of the things that they tried to implement. Makes a lot of sense. Failed miserably, actually. It's not deployed. Quality of service. Why can't I guarantee bandwidth on a call? Like, that seems like a problem that's really easy to solve. Why can't I reserve that 1 megabit per second connection? So this, again, if you're requiring changes into that IP layer, it's already too late. You'd have to change a whole bunch of stuff that's not getting changed anytime soon. The last thing is layering and abstractions that I want to cover. And this is actually everywhere, but it is particularly well done in the internet protocols. The separation of functionality into layers and then sort of the localization of the implementation at that layer allows you to then abstract the function away. And that is when you have layered something and have created a really strong abstraction to the functionality, you can start building stuff on top of that really quickly. And that's what you find applied to networks. So if you take the networking class, you'll see the multiple layers of the protocol stack. Basically, what applied to networks, there are sets of rules that govern communication between different elements of the networking stack. And then each layer relies upon services from the layer below it. So it's treating the layer below it as an abstraction, and then exports services to the layer above. It's being used as an abstraction for an upper layer. And you will see this in all sorts of computing systems. And I just wanted to point out the networking one because this is the layer, this is the case that we're going to be covering the next 3 weeks. So the big thing here is that the layer implementations can completely change without disturbing any of the other layers. Like if I have a program that uses TCP and somebody decides to go on my Linux machine and totally replace the implementation of TCP, as long as they haven't changed the abstractions that the TCP layer provides, I don't care. And this has actually happened multiple times on my Linux machine, right? Like all of a sudden, the kernel developers say, no, this algorithm is better than that algorithm for TCP. I'm just going to install it. And then everybody gets it without changing any of your applications. And that's really key. And you want that in anything you develop, right? Like any API, like any REST API that you want to develop and put out there, you want to make sure your abstraction and your layering is really tight so that you have the ability to improve your backend without causing someone to completely be inoperable, without having to deal with backwards compatibility issues. Okay. And this motivates what we'll cover, this protocol quick that we're going to cover in a couple weeks. Well, no, this doesn't motivate that. One of the disadvantages of layered implementations and layering all the abstractions on top of each other is that you have a performance hit. Every time you go from one layer to the next, you might have a context switch. You will definitely have a data copying overhead. Layers cost you. And so one of the things with networking protocols is that, you know what, we really know enough about how networking should be done to combine all of those layers into one enormous one. That's what this is, which is what we'll cover. And this is something that is now this got renamed to HTTP 3. So the next version of HTTP is going to be based on that. And so we'll cover that. We'll cover that in next week. Okay, so here's an example of layering that is specific to networks. Any topology and physical configuration that the network has is completely hidden to the application. When was the last time you saw an application try and query what the next hop router is? Or how many hops are there in Portland? How many hops are there to get out of Portland State? Like the application doesn't need any of that, right? It doesn't need to update any of its logic based on any changes that are happening in the network. And because of that, the way this works is because you have abstracted away the host-to-host connectivity. You say, I'm going to send a packet to this IP address, just deliver it. That's all that this is, and then this is an abstraction now. The whole internet protocol stuff is an abstraction as soon as I have an IP address that will deliver me a datagram. Even reliability is something that can be layered on top of this simple datagram service. And so these are abstractions that we'll cover. And so this really, as soon as you get the abstractions right, then anybody can start developing to them. And that's what happened. They had strong abstractions on the networking stack, and then now you can deploy applications without coordination with the network at all. Okay. So here is where I want to make a note that layering and abstraction extends all the way up to the machine, the operating system, the applications, and collections of all of these. So we'll show you the abstractions and layering of the networking stack, But when we get into the cloud, the abstraction is on operating systems and on machines and on clusters of machines. You will see that the abstraction layer can be wrapped around anything. And it's all about keeping track of what the thing is abstracting away in the cloud. Okay, so this is the basis, the reason why we're teaching the cloud stuff. So all of this, if you've paid attention to the buzzword around the industry, all this stuff about serverless. Serverless is a way of abstracting out machines, networks, and operating systems, right? I just want to program Python. I don't want to know about an IP address. I don't want to know about Ubuntu. I don't want to know Linux at all. Can I deploy my app without knowing any of that stuff? And yes, if I've abstracted away your network, your machines, I'll just, on demand, get you the compute that you need to run your app, then you don't need any of the lower layer stuff. So you won't need the first half of this course if you're sitting here developing on serverless applications that have abstracted the entirety of the first half of the course away. Now, that's the direction that we're going. Unfortunately, we've probably got decades worth of the old way of doing things. So you really need to know the old way of doing things, like networks and machines and Linux and that kind of stuff. But the idea of serverless and cloud applications is to move away from needing to know the lower layer abstractions. The abstraction level is eventually going to be, I just have a program, just serve it to millions of people, and give me the bill later. That's the important part, because yeah, you're going to get charged for that. Okay, so we are going to sprint through the internet protocols at the beginning of the course. And part of this is because in a lot of cloud deployments, you are taking just legacy machines and just pushing it into the cloud. And in order to do so, you need to know about IP addresses. You need to know a little bit about transport protocols because of the way we're going to map IP addresses to connections. You need to know a little bit about the specific application layers. So you'll need to know the guts of the protocol stack if you do one of these legacy things. So that's what we'll do. So the layers are here. This is the internet protocol stack. You'll see it has 2 less layers than the OSI stack. You basically have a physical layer, that's the hardware at the bottom. You have a link layer that is basically data transfer between 2 elements directly connected to each other. And this is basically like your Wi-Fi. The connection between you and the base station. That base station, that would be a data link layer connection. Or a wired Ethernet. I don't have a wired Ethernet, but that would be a hop-to-hop connection is what that layer takes care of. And then the network is the routing of datagrams from one logical address to another. And so this is where the internet protocol is, layer 3. The transport layer deals with connections from one machine to the other in terms of being able to identify, yes, this is a web request going to the web server on that machine versus this is a mail connection going to the mail server on that machine. It also deals with what happens if packets are lost in the network. So the transport layer is going to be like, hey, you've been sending me packets, but I don't have this packet. Can you send it again? That's the transport layer, an end-to-end protocol trying to make sure that you have an actual consistent connection. And we'll talk about the protocols for doing that. And then finally, you have the application layer. This is where you're saying, hey, I'm a web client talking to a web server. I connect up with the web server on a TCP connection, and I say to the web server, get me index.html. It's an application protocol. Or here's an email from me to someone. That's SMTP. So we're going to go through this protocol stack just very briefly at the beginning of this class. I want to give you a picture of how these protocols work, though, just visually, so that when we get into the details of what protocols are doing, you've got a reference point. I like to use this Russian doll analogy, and this is applied to any packets over the network. So in the middle is the application data. So this thing might be the URL that you are sending to the server saying, get me index.html. this thing is then encapsulated with a transport protocol that says, hey, you know what? I am a web server trying to talk to a web client, and these are the local addresses of the browser and the server on those machines. These are the port numbers that they're using. And so that's what the transport layer is doing. Sticking on that end-to-end transport segment header. And then this is then wrapped with a network packet. And the network packet just has an IP address saying this is the IP address of the destination that I'm sending to. And then the outermost DOL is that data link layer. I need to get it to the next hop. So from me to that base station, I need to put a frame around it so that it speaks, I'm guessing that's 802.11, so it speaks 802.11 to that base station so that it can then be decapsulated and sent as an Ethernet or a fiber, whatever is on the back end of that base station. I have no idea, actually. Probably Ethernet. It's probably an Ethernet thing. Okay, so you can think of all these protocols like a letter that you're sending from yourself to somewhere else. So the application data is the contents of the letter in the envelope. That's your URL, for example. It could be your, it's the contents of the letter in the envelope. The transport information is on the address on the outside. So it could be the recipient, the dorm room number, the apartment number, the carrier that you're using to transport that letter. You could use any sort of, U.S. Postal Service, UPS. That is the analogy to the transport layer protocols that we currently have. And this is equivalent in the transport layer to the process address, the process port, for example, like HTTP is port 80. That's part of the transport layer information. The packet sequence number might also be part of this if you have labeled your letter with certain sequence numbers. So that's the transport layer. The network information is just the street address, city, state, and zip code, right? So this is different than, for example, having a person. So if I send a letter to the Broadway dorm, I'm going to need this as the transport layer, the person and the dorm room number, but the actual network layer thing that the deliverer, the US delivery guy looks at is just this, okay? And then finally, the data link layer information. This is the vehicle or the person, the carrier, transporting the mail on a hop-to-hop basis in the system. So that is the analogy I want you to think of when you think of the networking protocols, because that's basically what's going on. Okay. So this is what happens when you send a URL over the internet. The first thing is that your web client will create the entire DOL. It will create the URL that you want to send. It'll create the transport layer, and it'll start to label it with sequence numbers so that it can know whether or not the server has properly received the segments that it's creating. What it's going to do, it's going to send that thing. It's going to have a timeout, and then it's going to wait for an acknowledgement for that packet. And if the timeout happens before the acknowledgement is received, it's going to send it again. So this is the transport layer being created in the end host. Then it creates the network layer packet. So it has figured out the IP address of the server that it's sending the URL to. So it has to slap that onto the packet. And then finally, in order to get to the very first hop of the network, it creates this data link layer frame and sends it directly to the base station or the default router. The router sees this entire DOL and says, you know what, I pulled this off of the data link layer of the incoming. I'm going to take that outer layer out, the data link layer frame out, and I'm going to put on a new one to go to the next hop. I'm going to look up, so I'm going to take out the data frame, and I'm going to look at the IP address of the packet, the destination that it's going to. I'm going to figure out where the next hop is, and then I'm going to put another data link layer frame on it to go to the next hop. So this is hop by hop going through the network. It's basically pulling off the data link layer header, looking at the IP address, putting a data link layer header back on, and then sending it to the next hop. Okay, so that's the Russian doll analogy. And then eventually the other side gets this and then decapsulates all of this and then sends any acknowledgments in the transport layer, parses the application payload. If it's got a URL, it processes it, forms a response, and then on the other side of that, it's a bidirectional connection. It'll start sending the content back. Okay. So that's the highest level what these protocols are doing. How much time do I get? I get 20 minutes as it goes to 350? Okay, so I'm going to finish early. Actually, you know what? I'm not. I need to actually do one other bookkeeping thing. I'm gonna start the data link layer in a second. But the next 2 weeks, 2.5 weeks, are a crash course on the Internet Protocol stack. If you've already taken the networking course, this is a little bit of review. One of the things. So